Okay, little disclaimer before we start. This over here that you see, this is not a division sign. Okay, that's a square root sign. So this is actually to say, for example, the square root of 16, which is 4, square root of 25, which is 5, right? So the proper division sign would have been this. But my program here, Microsoft Word, does not provide me with this symbol right here. A straight line this way and a straight line this way, which is the division sign. Okay, so just don't get confused, and definitely don't use this because that's the square root sign. All right, let's get this started. Question one: how do I know? Actually, you know what? I'm going to start with this one. And how do I know 74581 is or is not divisible by 11? Well, the rule for 11 states, or the trick for 11 that we did in class was I add the first, skip one, add a third, skip one, add a fifth. So I have 7 plus 5 plus 1, and that equals to 13. And then I add the leftovers, right? The 4, the second one, the fourth, and the fifth. And I get 4 plus 8 plus 1. And I add those and I get 13. And now if I subtract those, I get 0. So if your answers are 0 or 11, then this whole number here should work out, not should, it will work out without having any remainder. So let's see if that is actually true. So the answer to this was explain why it is or it's not. It definitely is because we did that little trick right now, and it is divisible by 11. So let's see if it actually is true. 11 divided by 7, 4, 5, 8, 1, 1. It goes 74 6 times, 66, subtract. 8, that's a 5, an ugly 5, but still a 5. We go 7 times, 77, subtract, 50 minus 7 is 8, bring the 8 down. It's 11 into 8 is 8 times, 88. Bring that 1 down, I'll bring it over here. 11 does not go into 1, so I put a 0 on top of that. Bring the other 1 down, and 11 goes into 11 one time. So final answer is 67,801. And if you had the time, you can actually multiply that times 11, and you should get 74,581. So you can always work back to see if you got it correct. Next one, again, this case, it says, how do I know if it's 8,445 is divisible by 15? Well, another way of looking at 15 is that 15 is the same thing as 3 times 5. So I can use the divisibility rule for 3 and for 5 to see if that's going to actually work out without any remainder. So divisibility rule for 3 states that if I add 8, 7, 4, 5, the digits here, 8 plus 7 is 15, plus 4 is 19, and plus 5 is 24. So if I add those numbers up, it's 24. Is that divisible by 3? Check. So 3 works. So let's check if it's divisible by 5. Well, to see if it's divisible by 5, we look at the last number. If it's 0, 5, it's divisible by 5. And it is. So check. So there. I just determined that it's going to be divisible by 15 because it worked for 3 and it worked for 5. Okay. So let's see if it actually works out. 8, 7, 4, 5. I'm going to say 6. No, 5. 75. Subtract, you get 2, 1, bring the 4 down. Ooh, 8, 0, 8 times. 8 times 5 is 40, carry 4, 120. Subtract, I'm going to have 4 left over, bring the 5 down. 15 goes to 45 3 times, and you get 45, remainder of 0. So I have this correct. 15 goes inside 8,745 583 times. I can make 583 groups of 15 inside of that. So I checked it with divisibility rules, and I checked it showing the work. Okay, so I need all this on both sides. Just not a yes here will not suffice. You actually have to write that you checked for 3 and 5 in this case, because 3 times 5 is the same thing as 15. Okay. In the number, and I'll write this number here with blanks. I'll remove the A and the B. So I have a 4, a 5, a blank, a 5, and a blank. So we need to fill these two. spots here with digits, so that whatever number it becomes, it's divisible by 2 and divisible by 3. So in order to be divisible by 2, this last number has to be a 0, 2, 4, 6, 8, right? So let's pick 0. So that checks, it's divisible by 2. Now, in order for it to be divisible by 3, I have to add all these numbers, and it has to be a multiple of 3. So far I have 4 plus 5, which is 9, plus this 5, which is 14, plus 0 is still 14. So to be a multiple of 3, well, 14 is not going to do it, but 50 definitely works. So 4 plus 5 is 9, plus 1 is 10, plus 5 is 15. So now I have this number, and I know it's going to be divisible by 3 because when I add them, it gives me 15, and 15 is definitely divisible by 3. So that's one option. Let's make another one. Blank, 5, blank. So again, it has to be divisible by 2 by 3. So to be divisible by 2 has to end in an even number. Let me pick, I don't know, 2. Pick the small numbers. So what do I have so far if I add these? I have 4 plus 5, which is 9. 9 plus 5, which is 14. And 14 plus 2 is 16. 16 is not divisible by 3, so what can I add to 16 to make it a multiple of 3? So 16, if I add 2, for example, I get 18. So 18 is divisible by 3. So this number here, I can add a 2. 45,252 is divisible by 2 because it's even, and because if I add all the digits, it adds up to 18, and 18 is divisible by 3. Okay. Next one, find all the factors of the numbers. And a lot of you actually found the factors of these numbers, but those are the question numbers. Okay, so don't do those. 36, well, 1 and 36. Go to 2 and 18, that works. 3 works too, 3 and 12. 4 and 9, then we have 6 and 6. 7 no, 8 no, 9's already written, so I know I have all my factors. 1, 2, 3, 4, 6, 9, 12, 18, 36. Is it a composite? Yes, it is, because it has more than 2 factors. Is it an IMERP? No, because it's not even prime to begin with. Is it a perfect square? Yes, because 36 is also 6 times 6. There is a way of writing 36 using two of the same numbers multiplied by itself. So 36 is a perfect square as well. 80. 1 and 80. 2 and 40. 3 is not going to work because 8 plus 0 is 0. It's not divisible by 3. 3 no, 4 yes. 4 and 20. 5 yes. 5 and 16. 7 no. 8 and 10. 9's a no, 10 already said it, so I know I have all my multiples. Again, there's a bunch of multiples. I'm sorry, a bunch of factors. And this is composite, more than 2 factors. It's not a perfect square, and definitely not an IMERP, because it has to be prime to begin with. Okay. 12, 1 and 12, 2 and 6, 3 and 4. 5 no, 6 I already said it, so here are all my factors. So this is definitely a composite again, not an IMERP, and not a perfect square. 17, 1 and 17, no 2's, no 3's, no 4's, no 5, no 6, etc., nothing. So it's just 2 factors, which makes this prime. Is it an IMERP? Yes, it is, because if I take 17 and reverse the digits, I get 71, which is also prime. So this is prime frontwards and backwards. So this is a IMERP. I don't even know if we're saying that right, but IMERP it is. Okay, so let's do the easy ones. 3 squared. Remember, squared is another way of saying to the second power. Expanded form is 3 times 3, and standard is 9. 7 times 7 times 7 is 49, right? 7 times 7 is 49 times another 7, and you're going to get 343. Word form, you can write 7 cubed, because to the third power you can use the special word cubed, or you can say 7 to the third power, that's okay. Exponential, 7 to the third power. 10 to the fifth is 10 to the fifth power. Expanded is 10 times 10 times 10 times 10 times 10. Okay, and it's 1 with 5 zeros. 1, 2, 3, 4, 5. That's just a little trick. Okay, that works with tens. All right, so 10 to the 5th is the same thing as saying 100,000. 125. Ooh, what number multiplied by itself several times will give you 25? Well, because it ends in a 5, a clue is it's going to be some type of 5, like 5, 15, or 25 or something. But it can't be 15 because it's too big, because 15 times 15 is already more than 125. 25 times 25 is also more than 125. So let's look at the smaller one. 5 works. Well, let's see if it works. 5 times 5 is 25. And 25 times another 5 is 125. So this one is going to be 5 times 5 times 5. Word form, 5 cubed. We can use cubed again, or 5 to the third power. And exponential form, 5 to the third. Okay. All right, let's see. If it's divisible, well, let's put an x. So is it divisible by 2, 120? Yes, because it's even. Is it divisible by 3? Yes, because if I add 1 plus 2 plus 0 is 3, and 3 is divisible by 3, so yes. By 4, look at the last two digits. Yes. By 5, ends in a 0. Yes. By 6, it worked for 2 and it worked for 3, so yes. By 7 is, let's see, the rule for 7 says, take the last number, double it. So if you double 0, you still get 0. Subtract it from the other two numbers. And 12 minus 0 is 12. Is 12 a multiple of 7? Is 12 in the 7 times table? No. So it's not going to work. 8. Is 120 divisible by 8? Well, this one you actually have to do it. 8 goes to 12 one time. Subtract, you get 4 left over. 8 goes into 45 times. So 8 is a yes. 9 is a no, because if you add them up, it's not divisible by 9. 10 is a yes, because it ends in a 0. 11, obviously no. And to see, 11 is a no. And for 12, if it worked for 3 and it worked for 4, it works for 12, so definitely yes. 781, 2, no. Not even. 3, no, because if I added, it gets 16. 16 is now a multiple of 3. 4, nothing in the times table of 4 ends in a 1, so it's a no. 5 is a no again. 6 is a no because it didn't work for 2 and 3. 7, is it divisible by 7? Well, let's take this. The divisibility for 7 is, take this last number, multiply that by 2, or double it, you get 2, right? 1 double 1 is 2, and then subtract it from the other numbers that weren't used, so 78, and you get 76. Is 76 a multiple of 7? No, so it's not going to work. 8. 8 is a no as well, because nothing in the 8 times table ends in a 1, so that's a hint. No. 9. 7 plus 8 is 15, plus 1 is 16. 16 is not a multiple of 9. No. 10 doesn't end as 0. 11. Ugh. Well, I know 12 it's not, because it didn't work for 3 and 4. But 11. Will it work for 11? Well, the rule for 11 is take the first one, take the last one, add those two. 7 plus 1. Then take the remaining, add it. Well, there's nobody to add, so it's just 8. And then subtract these two. 8 minus 8 equals 0. So if the answer is a 0 or 11, it's a multiple of 11. So if you actually have a calculator right now, you can divide 781 by 11. You'll get a nice whole number. 416. 2 is a yes. 3 is a no because it doesn't add up. 4 is a yes. Because if you look at the last two digits, 16 is a multiple of 4. 5 is a no. 6 is a no because for 6 you have to work for 2 and 3. So 3 didn't work for 3, so 6 is no. 7, again, for 7 you would do 416. You would double 6. If I double 6, like times 2, you get 12, right? And then I subtract that from 41. I get 29. 29 is not a multiple. It's not a multiple of 7, so that's 7 to no. 8. 8, you actually have to do it. 416 divided by 8, because you have to look at the last three numbers. 8 goes into 41 5 times, which is 40. Subtract 1 left over, bring the 6 down. 8 goes into 16 2 times. So for 8, it did work. 9, add them up. 4 plus 1 plus 6 is 11, so no. 10 is a no. 11, well, it's 4, 1, 6. So you take the first one and the third one, add them up. 6 plus 4 is 10. The 1, you're going to subtract, right? And then you get a 9. 9 is not a multiple of 11. Sorry, 9 is, your answer has to be a 0 or 11. So because we got a 9, it tells you it's a no. For 12, it had to work for 3 and 4. It didn't work for 3. It only worked for 4, so it's a no. So that's it. List the first 15 prime numbers. Oof, let's see if I can do this. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. Oh, there's only 10 here. 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47. There. I think there's 15 over here. Prime factorization of 840, so we're going to go like this and rewrite 840 using only prime numbers, multiply as a product of only prime numbers. So 840 divides into 2. Let's see, we can use 84 and 10. 10 breaks into 2 and 5. 2 is a prime, so I circle. 5 is a prime, so I circle. 84 would be 12 and 7. 7 is a prime, I circle. 12 I can break up into 2 and 6. 2 I circle, and 6 becomes 2 and 3. So you can tell now that I only have prime numbers left at the ends. So 840 is another way of saying 840 is 2 times 2 times 2 times that 3 times that 5 and times that 7. Better yet, 2 to the third power times 3 times 5 times 7. This is the answer I'm looking for. Prime factorization of 180. Break it up into 18 and 10. 2 and 5. 18 is 2 and 9. And I'll break the 9 to 3 and 3. So I get a 2 times another 2 times another 3 times another 3 and times another 5. You get 2 to the second power times 3 to the second power times 5. Finally, we have a number that's less than 100 that has exactly 6 factors, one of them which is 15. So this confused some of you guys. So here's a number that I don't know. Okay, it's a mystery number that has 6 factors. 1, 2, 3, 4, 5, 6. So if I go this times this, this one and that one gives me 15. If I multiply this times this, it gives me I multiply this one times this one, gives me my mystery number. If I multiply the second one and the fifth one, it gives me my mystery number. And I multiply these two, the third and the fourth, it gives me my mystery number. One of these numbers is 15. Okay, so one of these 6 numbers is 15. So use that. So I'm going to do something here. So if I put 15 here, it means that this is a 1, right? So 1 and 15. Would that work? Well, if this is 1 and 15, it means that our mystery number is now 15, because 1 times 15 should give our mystery number, right? Other factors of 15, 3 and 5. Is there anything else? No. So definitely 15 is not our number. Okay, so let's erase this. All right, so let's put the 15 in some other place. Let's put the 15 here, not instead of the end. Let's put it there. And so you got 1 times something is our mystery number. Let's use 2 over here. 2 times 15 gives our mystery number. 2 times 15 is 30. So let's see if 30 is our number, which makes this 1 and 30 all the way here. 2 and 15. Is there a 3? Yeah. 3 and 10. 4, 5 and 6. So there's a 5 and 6. So this 30 has more than 6 factors. So it's definitely not our number again. So let's erase that. So that's not going to work. Let's try 3. So let's put the 15 over here. Leave it over there. And instead of 2, let's try 3. 1 and something, 3 and 15, and 3 times 15 is 45. So let's see if our number is 45. Go back from the beginning. So our first two factors will be 1, it's 45. 2 is not going to work because it's not even. 3 works, 3 and 15. 4 no, 5 is going to work, 5 and 9. 6 no, 7 no, 8 no, 9 no, 10 no, 11 no, 12, 13, 14, 15 is already here, which means all my factors are listed once I repeat it. So 1, 3, 5, 9, 15, and 45, that's 1, 2, 3, 4, 5, 6 factors. Good. And we found our number. So here is our mystery number, who has 6 factors, one of them of which is 15. Okay. Always, sometimes, or never. So is the sentence always true? Sometimes true, or never true? The GCF of two numbers is always greater than those two numbers. Well, let's pick two numbers. 4 and 10. Let's see if that's true. To find the GCF, let's use the ladder method. You know what? I won't. The GCF, let's list all the factors. 1 and 4, 2 and 2. The 10 is 1 and 10, 2 and 5. That's it, right? So the GCF here is what? 2, because that's the greatest number that they share, right? The GCF of 4 and 10 is 2. Is it greater than 4 and 10? No, it's not. So think of another example. You need to find an example that will validate this sentence for it to be true, at least sometimes. So in our first example, the GCF was not greater than both numbers. Pick another two numbers, any two numbers. 10 and 20. This time I'm going to use the ladder method. GCF of 10 and 20. 2 goes into 10 5 times. 2 goes into 20 10 times. We can go again. 5 goes into 5 1 time. And 5 goes into 10 2 times. What's our GCF? Here, the GCF is a product of those two numbers. 2 times 5, which is 10. The GCF is 10. Is 10 bigger than 10? No. Is 10 bigger than 20? Also no. So it doesn't seem like our GCF is going to be bigger than these two numbers. So the first sentence is probably, not probably, but it's never true. The GCF is never greater than the two numbers that we're comparing. LCM. The LCM of two numbers is always equal to one of those two numbers. Well, let's find the LCM. Let's pick two numbers, 4 and 10. Find the LCM, we list multiples. 4, 8, 12, 16, 20, 24, so forth. 10, 20. Here's our LCM, which is 20. Is the LCM of 20 equal to either 4 or 10? No. So far it looks like that sentence is never true. Can you find an example where it actually might be true? Let's try 2 and 4. Multiples of 2. 2, 4, 6, 8, 10, so forth. 4, 8, 12, 16, 20, so on and on. What's the LCM? The first number that shows in either times table is 4. Is 4 equal to one of our numbers we're comparing? Yes, it is. So there are times where the LCM is actually going to be equal one of the two numbers. But this could be sometimes true. So the first one was actually never. The second one is sometimes. So you need to work out, you need to find examples that actually will validate the sentence or not validate the sentence, or validate the sentence sometimes. A number squared has the same answer as the number multiplied by 2. So a number squared, 3 squared. 3 squared is 9. So it's saying that a number squared has the same answer as that number multiplied by 2. So if I took 3 and multiply by 2, I get 6. Is multiplying a number by 2 the same thing as raising it to the second power? No, it's not. Can you find an example where it actually might be? Let's try 4 to the second power. 4 to the second power is 4 times 4, which is 16. What about 4, just doubling or multiplying 4 times 2? 4 times 2 is 8. So in this case, it's not the same thing. 2 to the second power. 2 to the second power is 2 times 2, which is 4. What is 2 multiplied by 2? It's also 4. So in this occasion, I'm pretty sure it's the only one, it actually gives you the same answer. Where squaring it, or raising it to the second power, or multiplying by 2 gives you the same answer. So this would be sometimes. All perfect squares have 3 factors. Is that true? Well, a perfect square are numbers like this, because 6 times 6, so 25 is another perfect square, but you can get 5 times 5. 16 is another perfect square because it's 4 times 4. So these are perfect squares. Numbers that have 2 factors that multiply give you that number, but they have to be the exact same number. So 9 is another perfect square because it's 3 times 3. So some numbers that have those characteristics are called perfect squares. So all perfect squares have 3 factors. Well, let's see. 9. Factors of 9. 1 and 9. 3 and 3. So 3 factors. True. Let's try 16. 1 and 16. 2 and 8. 4 and 4. Uh-oh. 16 has 5 factors. So it's not true for 16. Let's try 25. 1 and 25. 5 and 5, so just 5. 25 has 3 factors. So sometimes it looks like a perfect square has 3 factors, like 9 and 25. But sometimes, like 16, it has more than 3 factors. So all perfect squares have 3 factors is sometimes true. Okay, so see how you did. Hopefully you did well. And good luck on Monday. Let me move this away.